In this video, I will discuss some electrostatics problems from previous year's question papers of IIT JEE. This is the first question. A positively charged thin metal ring of radius r is fixed in the xy plane with its center at the origin O. A negatively charged particle P is released from rest at 0, 0 z0, where z0 is greater than 0. Then the motion of P is option A, periodic for all values of z0 satisfying z0 greater than 0 less than infinity. Option B, simple harmonic for all values of z0 satisfying z0 greater than 0 less than or equal to capital R. C, approximately simple harmonic provided z is much small compared to R. D, such that P crosses O and continues to move along negative z towards z equal to minus infinity. You can pause this video and attempt this question. Here is the solution. So the ring is kept in the xy plane and a negatively charged particle of charge minus q is at a distance z0 along the z-axis. So there will be a force of attraction between this point charge and the positively charged ring. So if you take a small element of this ring, the direction of force will be along this direction, and all the elements of force will attract this point charge in different directions, but the cos component, that is the component along the z-axis, will add, and the component perpendicular to the z-axis will cancel. So it's as if the full charge is concentrated at a point and the z component of that force is the net force. So the force acting on this negative charge minus q is k, where k is 1 by 4 pi epsilon naught. The product of the charge is q and capital Q divided by the distance. The distance is this distance, which is the radius r square plus z0 square and square root of it. This is the Pythagoras theorem. And the cos component of this force, that is cos alpha, and cos alpha is adjacent side, that is z0 divided by square root of r square plus z0 square. So this force is approximately kqq into z0 divided by rq, for z0 much smaller compared to r. When z0 is much smaller compared to r, the z0 in this term and this term can be neglected, so it will become rq. So under this condition, the force acting on this minus q is proportional to the displacement z0, which is a requirement for simple harmonic motion, and it's towards the equilibrium position, the mean position. So for z much less than r, the motion will be like an SHM. So option C, which says it's approximately simple harmonic provided z is much less than r, is true. Option B says simple harmonic for all values of z0. That is not true, because for z0 not very small, there is a general expression which is not linearly varying as the displacement. Option D says so that P crosses O and continues to move along negative z up to minus infinity. After it crosses this z equal to 0, it will start facing a retarding force because the force of attraction will be towards the origin. So the velocity will keep on decreasing, and after that it will turn back. It will turn back at z equal to minus z0. It will turn back and will come up to plus z0 and will keep oscillating. So option D is not true. Option A says it's periodic for all values of z0. Yeah, it's periodic because it's an oscillating motion, and the oscillating motion is a periodic motion. So the correct options are option A and C. This is the next question. A non-conducting solid sphere of radius r is uniformly charged. The magnitude of electric field due to the sphere at a distance r from its center is option A, increases as r increases for r less than capital R. B, decreases as r increases from 0 to infinity. C, decreases as r increases from capital R to infinity. D, discontinuous at capital R. You can pause and attempt this question. Here is the solution. So it's a non-conducting solid sphere which is uniformly charged and let the charge density rho. So you have to find the expression of electric field at any general point outside and inside. electric field at a point outside. It's as if the fold charge is concentrated at the center as a point charge. This is a standard concept we are using. So it is K into 4 by 3 pi r cube into rho, that is the total charge, divided by r square. So it's proportional to 1 by r square. Electric field at a point inside is K into the charge which is present inside, that is 4 by 3 pi r cube into rho divided by r square. So it's proportional to r. So this results we can get also by using Gauss's law. So these are standard results. So the variation of electric field as a function of r will look like this. It will linearly increase from 0, r equal to 0 to the surface of the sphere, and after it will go down as 1 by r square. So the option A says increases for r less than capital R, that is true. Option B decreases for all r, that is not true. Option C decreases for r outside, that is true. Option D discontinuous at r equal to capital R. Electric field is continuous at r equal to capital R. So D is not true. So the correct options are option A and C. This is the next question. An elliptical cavity is carved within a perfect conductor. A positive charge Q is placed at the center of the cavity. The points A and B are on cavity surface as shown in the figure. Then option A, electric field near A in the cavity is equal to electric field near B in the cavity. Option B, charge density at A equal to charge density at B. Option C, potential at A equal to potential at B. Option D, total electric flux through the surface of cavity is Q by epsilon naught. You can pause and attempt this question. So here we use a known concept. Suppose we have a spherical conductor, perfect conductor, and it has some charge. So all the charge will move to the surface. The potential of this conductor is given as K into Q by R, where Q is the total charge, that is 4 pi r square into sigma. Since it is a perfect conductor, all the charges will move to the surface, and at the surface charge is to be sigma. So from this we get a result that the potential is proportional to sigma into r. So if the radius of sphere decreases, then the surface charge density will increase for the same potential. So this right one is a smaller sphere of same potential V, and at its surface charge density will be sigma 2. So sigma 2 will be greater than sigma 1. So now if we take a conductor of this general shape where the radius of curvature is changing, the radius of curvature is small r at this right side, and on the left side is capital R, which is radius of curvature here is more, and here on the flat surface the radius of curvature is very large, approximately infinity. So here the surface charge density will be more on the sharp side. So this result we will use in this problem. So the radius of curvature at point B is small, so more surface charge density will be here, and less number of surface charges will be here at point A. So the electric field at point A will be less than electric field at point B. So option A is not correct. Option B says charge density is same. That's not true. It's inversely proportional as radius of curvature. Option C says potential at points A and B are same. That is true because inside a perfect conductor, the potential at all points are same. If it is not same, there will be an electric field which is not allowed. Option D, the total electric flux through the surface of cavity. The electric field lines will start from this point Q and will terminate on the surface. So do not cut the surface. So electric flux is related to electric field lines passing through the surface. So since the electric field lines are not cutting the surface, it's as if the total electric flux is 0. So option D is also not correct. So the only option is option C. This is the next question. For a spherically symmetric charge distribution, variation of electric potential with distance from center is given in diagram. Given that V equal to Q divided by 4 pi epsilon naught R naught for R less than R naught, and it's equal to Q by 4 pi epsilon naught R for R greater than R naught. Then which options are correct? Option A, total charge within 2R0 is Q. Total electrostatic energy for R less than equal to R0 is 0. At R equal to R0, the electric field is discontinuous. There will be no charge except at R equal to R0. You can pause the video and attempt this question. Here is the solution. Electric field is related to the potential as the gradient of the potential, the negative gradient. Inside the electric field, there is no gradient, so electric field is 0 for R less than or equal to R0. And for outside, the expression for potential is given like this: Q by 4 plus 1 by R. So derivative of this will give 1 by R square. So this is the variation of electric field outside. Option A says the total charge within 2R0 is. This we can obtain by using Gauss's law. Since it's spherically charge distribution, the electric field, the total electric flux is the electric field, which value is Q to 4 pi epsilon naught into 1 by R square into the surface area 4 pi R square, that is equal to Q in by epsilon naught. So from this we get Q in as Q. So option A is true. And option B says the total electrostatic energy for R less than R0 is 0. Inside the electric field is 0. If the electric field is 0, there is no electrostatic energy. So option B is also true. Option C is the electric at R equal to R0, the electric field is discontinuous. Electric field is gradient. We have calculated the expression, so if you plot it, it will look like this. It is 0 for inside, and on the surface we have to put capital R. So we'll jump to this value, and after we'll go down as 1 by R square. So option C is also true. Option D, there is no charge except at R equal to R0. This we can apply by using Gauss's law. If we take a Gaussian surface slightly greater than R0, we will get the expression for Q in as Q, and any radius greater than R0 will still be Q. So all the charge Q is on the surface. So option D is also true. So all the options are true for this question. This is the next question. Two non-conducting solid spheres of radii r and 2r have uniform volume charge densities ρ1 and ρ2 respectively. Touch each other. The net electric field at a distance 2r from the center of a smaller sphere along the line joining the centers of the sphere is 0. Then the ratio of ρ1 by ρ2 can be. 4 options are given. You can pause the video and run this question. So these are the two non-conducting spheres of radius r and 2r of volume charge densities ρ1 and ρ2. So the point which is a distance 2r from the center of the smaller sphere, it can be either towards left or towards right. So the point towards left, P1, at a distance of 2r will be outside, and towards right at a distance of 2r from the center of smaller sphere will be here at a distance of r from this outer surface. So we have to find electric field at points P1 and P2. Electric field at point P1 is outside of both the charges, so it will act as a point charge. So it is K into the total charge 4 by 3 pi r cube into ρ1 divided by the distance square. So this distance is 2r square, and the electric field due to this bigger sphere is K into the volume 4 by 3 pi radius cube, that is 2r cube, into ρ2 divided by the distance of it from its center. So this distance is phi r. This radius is 2r and this diameter is 2r and this distance is r. So total is phi r. So phi r square, and this electric field should be equal to 0. So most of the things will cancel. So we get ρ1 by ρ2 as minus 8 by 25 into 4. So that's minus 32 by 25. So option B is true. Electric field at point P2, similarly we can find out. For point P2, the smaller sphere, electric field due to it can be calculated using as if it's a point charge located at the center. So that is at a distance of 2r from P2. So this is the electric field. And for the bigger sphere, the charge only inside sphere of radius r will contribute to the electric field at point P2. So the charge that's going to contribute will be 4 by 3 pi r cube into ρ2 divided by the distance r square. This should be equal to 0. So from this we get ρ1 by ρ2 as 4. So D option is also correct. So the correct option is option B and D. This is the next question. Prove conducting spheres, non-conducting spheres of radii R1 and R2 carrying uniform volume charge densities plus rho and minus rho respectively are placed so that they partially overlap as shown in the figure. At all points in the overlapping region, option A, electrostatic field is 0, B, electrostatic potential is constant, C, electrostatic field is constant in magnitude, D, electrostatic field has same direction. You can pause and attempt this question. Here is the solution. So for this problem we will use the standard result. If you have a non-conducting sphere of uniform volume charge density rho, the electric field at any point inside at a distance r that can be found using Gauss's law. So E into R into 4 pi r square is the total electric flux coming out, that is equal to Q in by epsilon naught. So from this we get the electric field inside is rho by 3 epsilon naught into R. So now we have to find the electric field at this point P, so which is inside of the sphere of charge density rho and also minus rho. So the electric field at point P is due to the electric field at due to plus rho and minus rho. Let's call it E1 and E2, and it's proportional to R from this relation, and E1 plus E2 will be EAP. E1 is proportional to AP, the distance AP, and E2 is proportional to the distance PB, and EAB is proportional to the distance AB. So AP, PB and AB are forming a triangle. So E1, E2 and EP will also form a triangle. It will be a scaled version of the triangle APB. So, and EAB, the direction is uniform for all the points in this overlapping region, and the magnitude is also constant as it depends only on the distance AB. So the option C, which says electrostatic field is constant magnitude, is correct, and option D says the direction is same. That's also true. So the correct option is option C and D.